All right, lesson 1.3 is the rates of change in linear and quadratic functions. And it starts out again talking about the average rate of change and the secant line. So just remember that your average rate of change is the same thing as your slope. And so it's still just our y2 minus y1 over x2 minus x1, but they showed the ordered pairs looking a little different there. All right, let's go ahead and look at example 1. It says find the slope of the secant line from the point -2, -6 to the point 3, 4. So we're after the slope of the secant, so we're just looking for our average rate of change there. So our average rate of change is equal to, let's do my skeleton. I'll go ahead and label my points. So my y2 minus my y1 over my x2 minus my x1. And so I know my average rate of change is 2. And it tells me, it says the slope of the secant line is also known as, so the slope of the secant line is the average rate of change over the interval -2 to 3, our x1 to our x2. All right, let's go on and look at example 2 there. It says for the function g of x equals x plus 4 times x minus 2, find the slope of the secant line from the point -1 g of -1 to the point 2 g of 2. Remember, it's always like g of x. So when they write like g of -1, that's the same as saying g of x, where x is -1, which we can see there, okay? All right, so I need to find my ordered pairs. And so I know it's going to have -1 comma some y. It's going to have 2 comma some other y. All right, so this is my x1. I've got to find y1. This is my x2, and I got to find y2. So remember, we talked about to find y1, we're going to plug x1 into our function. So it's just going to be -1 plus 4 times -1 minus 2, which is what, 3 times -3 or -9. And then to find y2, we just plug in our x2. So we have 2 plus 4 times 2 minus 2, which is what, 6 times 0, so it is 0. And to find the slope of the secant line, we're after that average rate of change there. So our average rate of change, do my skeleton, y2 minus y1 over x2 minus x1. So I get 9 over 3, which is 3. All right, and then rates of linear functions. Just remember the average rate of change over any length input value interval is going to be constant, and the rate of change of the average rates of change of a linear function will be 0. So if you're doing the rate of change of the average rates of change, since they are the same over the interval, it'll be 0 because it's not changing. All right, let's look at example 3. It says a table of output values of the function f is given for equal length input values. Find the average rate of change over the given intervals. So we're looking from -2 to 1, -1 to 0, 0 to 1, and 1 to 2. So the first one is going to be -2 to -1. So here is my 2 ordered pairs. So my x1, y1, my x2, y2. And so the average rate of change is going to be 5 minus 7 over -1 minus -2. So I get -2 over 1, which is -2. Then we're going to look from -1 to 0. So we're using these 2 ordered pairs. So I'm going to let this be my x1, y1, and the bottom one be my x2, y2. So when I find that average rate of change, I'm doing 3 minus 5 over 0 minus -1. So -2 over 1, which is -2. Then we're going to look from 0 to 1. I'm gonna let the top one there be my x1, y1. The bottom one be my x2, y2. So for my average rate of change, I have 1 minus 3 over 1 minus 0, negative 2 over 1, which again is negative 2. And then the last one there is from 1 to 2. So I have my x1, y1, my x2, y2. So it's going to be negative 1 minus 1 over 2 minus 1. So I get negative 2 over 1, which is negative 2. And so we can see there that the average rate of change of f of x is constant. It's negative 2 in each interval, which also tells us, according to the last little box we had read there, so that the rate of change of the average rates of change is going to be 0 because it's not changing here. All right, so if I found the slope of these, we would see that, well, negative 2 to negative 2, there's no increase. No increase or decrease. No increase or decrease. So the average rate of change of the rate of change is 0. All right, rates of quadratic functions. It says the average rate of change for a quadratic function will not stay the same. The average rates of change over consecutive equal length input value intervals form a linear pattern in a quadratic function. So if you look at the change in the average rates of change, you'll notice that it's constant, so it'll be a linear pattern. All right, the average rate of change is changing at a constant rate, and this means that second differences are constant. So what are second differences? Well, I'm going to use the table above real quick, so let me erase this. So just real quick on what they're talking about second differences, and we'll see it in a minute, was if I make sure, I need to make sure that my x's are in equal length intervals. If not, for my first differences, I need to use the slope formula. So when I go through here, notice all my x's are increasing by 1, and so I can look here and say, okay, well, my second difference is here. How do I get from 7 to 5? I subtract 2. 5 to 3, we subtract 2. 3 to 1, subtract 2. 1 to negative 1, subtract 2. Not a coincidence that those are the same numbers, okay? That was first differences. If those are the same, then my function is linear. If those are not the same, then I can do it again to those numbers. So I would find second differences. I don't need to on this one because this one's obviously linear. I'd find second differences, and if those are the same, it's quadratic. All right, and then if it wanted me to find, if it was cubic instead, I could find third differences or fourth differences to see if it's quartic. Okay, we could just keep going, but the more data, we would have to have more data in order to do it. All right, so let's look at example 4. Oops, sorry. Example 4, it says, given that g of x is equal to negative x squared plus 4x plus 1, shown at the right, find the average rate of change of g from x is negative 1 to x is 3. So again, I'm going to go find those ordered pairs. So I know it's going to be negative 1, comma some number, 3, comma some other number. All right, so to find their y values, I'm going to plug it in. Let's see, we got to find y, so I'm going to let this be x1, y1, x2, y2. So to find our y1, let's plug in x1. So we have a negative x squared. Now look at this real quick, guys. So you got negative, and then it's the x squared. So be careful because the negative 1 there, they were plugging it in, has to be squared. And then we put that negative from the very beginning back in front of it. So that's where a lot of people make mistakes. So we work this out. We get what? A negative. This gives us 1 minus 4 plus 1, which is negative 4. And we're going to find y2. So it's negative x squared plus 4x plus 1. This time my x2 is 3. So it's going to give me negative 9 plus 12 plus 1. So it's 3 plus 1, which is positive 4. And then I'm going to find my average rate of change. So my y2 minus my y1, my x2 minus my x1. That gives me what? 8 over 4, which is 2. And then part B says find the equation of the secant line containing those 2 points we just found, and then sketch it on the given graph. So remember, we did one like this in 1.2. So we know we know 2 points. So I'm just going to pick one of them. So I'm just going to use the first one. And we know our average rate of change, also known as our slope. And so we can use that point slope form. Oops, sorry, it's y minus y1 equals m times x minus x1. Which remember, we plug in x1, y1, and we plug in m. So I have y minus negative 4 equals 2 times x minus negative 1. Okay, I'm going to deal with my minus and negative. So y plus 4 equals 2 times x plus 1. I'm going to distribute my 2. And then I'm going to solve for y. And so the equation of the secant line is y equals 2x minus 2. And then it said to sketch it on the graph. Well, remember, with linear functions, it's y equals mx plus b, where m is your slope and b is your y-intercept, which is your starting point. So I know here that my slope is 2 and that my y-intercept is at negative 2. So I'm going to start at negative 2, and then I'm going to use my slope. I'm going to go up 2, right 1. Well, can't get my pen to write. There we go. Up 2, right 1. Up 2, right 1. Up 2, right 1. Or we could go down to left 1. And so here is my secant line. And you can see it goes through the 2 points that we used. So here is that point negative 1, negative 4, and there is the point 3, 4 that we used. All right, moving on to example 5. It says selected values for several functions are given in the tables below. Determine if the function could be linear, quadratic, or neither, and justify your answer. All right, so here we're going to look at differences. So remember, if our first differences are the same, because linear is x to the first in it, then it would be linear. Quadratic is x squared, so that's if our second differences are the same. And then neither will be, well, if neither one of those happen. All right, so but you have to make sure to look at the x's first. Make sure your x's are equal distance from each other, or it's not going to work, okay? If they're equal distances from each other, then you can just look at the y values. If the x's are not equal distance, the first difference is you need to use your slope formula or your average rate of change formula, and then you can just look at, for second differences, you can just look at the differences in those numbers. So on A, I'm going to look at it. So 1 to 3, I'm adding 2. 3 plus 2 is 5. 5 plus 2 is 7. 7 plus 2 is 9. So my x's are equal differences. So I can just look at these y's. So how do you get from 2 to 3? I'm sorry, 2 to 5. Darn, I said it out loud. We add 3. 5 to 9, we add 4. 9 to 14, we add 5. And 14 to 20, we add 6. Those numbers are not all the same. This is not linear, okay? So then we look at second differences. So we're going to find the differences of these. How do you get from 3 to 4? You add 1. 4 to 5, you add 1. 5 to 6, you add 1. Second differences are the same, so therefore this is quadratic. So we're going to say that this is quadratic. And it says to justify your answer, it's because second differences are constant. All right, then check out B. Check out your x's first though, remember. 0 to 2, we're adding 2. 2 to 6, though, we add 4, and then we add 6, and then we have to add 8. They're not the same. So I can't just do, how do I get from negative 2 to 0, okay? I'm going to have to use the slope formula to find those first differences. If they are all not the same, Then I can do like I did in A to check the second differences, because by using that slope formula, we're making it where the x's are like they are a constant difference between them. All right, so we're just going to use our slope formula to find the first differences. So between when x is 0 and 2, my y2 minus y1 over x2 minus x1 gives me 2 over 2, which is 1. All right, then between 2 and 6, I got 4 minus 0 over 6 minus 2. 4 over 4 is 1. Ooh, this is looking promising, but I got to check the others. All right, so now between when x is 6 and 12, so 10 minus 4 over 12 minus 6, 6 over 6. And then between the interval from 12 to 20, so 18 minus 10 over 20 minus 12 gives me 8 over 8, which is 1. These are my first differences. They are constant, so therefore this is linear. So, first differences are constant. All right, and then let's try the last one there, C. So check out your x's. 1 to 4 is 3, 4 to 7 is 3, 7 to 10 is 3, 10 to 13 is 3. My x's are good. So when I do this, how do we get from 81 to 27? Well, 81 minus 27, we're subtracting. 81 minus 27 is 54. So we're going to subtract 54. And then 27 minus 9. So we would have to subtract 18 to get from 27 to 9. 9 to 3, we would subtract 6 to get there. And 3 to 1, we subtract 2. This is not linear. First differences aren't the same. Then check second differences. How do you get from negative 54 to negative 18? Well, I'm getting closer to 0, so I'm adding something. So I'm going to take negative 54 minus negative 18, and I'm going to add 36. All right, negative 18 to negative 6. I'm getting bigger, so I would add 12, and negative 6 to negative 4, I would add 2. So this is not quadratic either, because second differences are not constant. So this is neither. And so the reason is because we could say average rates of change are not constant. So average rates of change are not constant. Okay, and we can say that because first differences is the average rate of change of the values, okay, of the figure, of the problem. Second differences is that average rates of change of the average rates of change. So technically they're both still average rates of change, okay? They're just of different data. That's the word I was looking for a second ago. Of different data, okay? So, but since neither one of those are the same, it's going to be neither of them. All right, moving on. More about concavity. So remember, it's concave up when the average rates of change over equal length input value intervals is increasing. Increasing is going up. So if your average rates of change are increasing, it's concave up. If your average rates of change are decreasing over equal length intervals, it's concave down. All right, so example 6 says selected values for several functions are given in the tables below. Determine if the function could be concave up, concave down, or neither. Justify your answer. All right, so let's look at those average rates of change, okay? Now, that means I can look at the first differences. I could just look at these first differences if my x's are in equal length intervals. If not, I need to find the slope. okay? So when I look at A, my x's are in equal length intervals. And so how do we get from 12 to 8? We subtract 4. 8 to 5, we subtract 3. 5 to 3, subtract 2. 3 to 2, we subtract 1. Now be careful here, this is a tricky part. When you look at those first differences there, when you look at those average rates of change, as we go down our table, are our numbers getting bigger or smaller? Well, as we are going down that table, -4 is smaller than -3, which is smaller than -2, which is smaller than -1. So we're getting bigger, okay? So these, as we go down this direction, they are increasing. And because they're increasing, that tells me what about concavity? That this is concave up. Because the average rates of change are increasing. Oops. All right, look at B. B, check out your x's. They're in equal length intervals, okay? So I'm just going to look at first differences. How do we get from 11 to 8? Subtract 3. 8 to 5. Subtract 3. 5 to 2. Subtract 3. 2 to -1. Subtract 3. What does it mean when first differences are all the same? Remember, that means it's linear. Does a linear function have concavity? Does it look like a cup or look like a frown? It does not. So therefore, this one would be neither. And why is it neither? Well, because the average rates of change are equal. This first differences are the same. This is a linear function. And remember, linear function is not going to be concave up or down. All right, let's check out C. All right, so look at the x's. They're in equal length intervals. They're each increasing by 5. So let's look at the p of x here. So how do you get from -3 to 6? You add 9. 6 to 11, you add 5. 11 to 13, you add 2, and 13 to 14, you add 1. So look at these numbers. As we go down our table, are those numbers getting bigger or smaller? These are getting smaller, which means they're decreasing. And if my average rates of change are decreasing, remember, that's the definition of concave down. So this is concave down. And that's because the average rates of change, the average rates of change are decreasing. All right, in example 7. Example 7 says the table below gives values of a quadratic function and selected values of x. Find the value of the constant k in the table. All right, so it told us that this is a quadratic function, which means our second differences are going to be equal. So let's go through and see what we can find. Well, we don't know. Well, first, check your x's. So from 1.5 to 1.9, we're adding 0.4. 1.9 to 2.3, we're adding 0.4. Check it out. To 2.7 is adding 0.4. To 3.1 is adding 0.4. So my x's are constant. They've got a constant rate of change going on there. So we're not going to be able to tell right now how to get from 3 to k because we don't know what k is, and that's what we're trying to find. And we also can't tell from k to 17. But 17 to 21, we know we're going to add 4. And 21 to 23, we add 2. But remember, this is quadratic, so we're looking at second differences. And so when I look at these second differences, again, when I look between these two, I can't tell. I also can't tell right here, but between 4 and 2, we would subtract 2. All right, so what would make this right here a minus 2? Because second difference has to be the same. Well, if I go backwards, 2 plus 2 would give me 4, right? So then plus 2 would give me 6. And then for this to be a negative 2, I would have to add 2 to go backwards, which would be 8. Okay. Now, let's see. Let me erase some of those circles, if I can do it without erasing everything else. No, I can't. I forgot. Wrong program. Okay. So we're going to do the same thing. Let me change colors. I'm going to go to red here. Same thing, looking now at our m of x column. So if I had 23, I would subtract 2 to give me 21. Minus 4 would give me the 17. As we're subtracting as we go up, okay? So then 17 minus 6 is 11. So I think k is 11, but let me check. 11 minus 8 would give me 3. So it did work. So we know that k is 11. All right, and that is the end of lesson 1.3.